So welcome everyone. Let me introduce the first speaker, who is Dagne Hordofa Tola, who earned his PhD in Statistical Physics in Addis Ababa in Ethiopia in June 2025. Nowadays, he is an assistant professor of physics at Dawa University, still in Ethiopia. His research is in collaboration with Professor Mulugeta Bekele and focuses on non-equilibrium statistical physics, with particular emphasis on non-equilibrium phase transitions, employing a combined methodological framework that integrates Monte Carlo simulations with modern machine learning techniques. Today, he will give a talk, and the title is Deep Learning Investigation of Non-Equilibrium Phase Transition in Ferromagnetic Systems with Effective Interactions. So, Daniel, you can start. I remind you that you have 25 minutes, more or less, plus 5 for questions. Thank you.
Thank you. Can you see my screen?
Yes.
Yes.
Okay. Thank you very much for a kind introduction. Today I'm going to give a talk on deep learning investigation of non-equilibrium phase transitions. Of course, before discussing the scientific results, let me briefly introduce the context of the environment. As introduced, yes, I'm from the Department of Physics at Dawa University in Ethiopia. For those less familiar with the region, Ethiopia is located at the Horn of East Africa, and Dawa is also in the eastern part of the country, somewhat close to Djibouti. Unfortunately, we do not have research facility in Dawa University, but we are working in collaboration with Addis Ababa University. Addis Ababa is our capital city, and this city is the home of many international organizations. Ethiopia in scientific context, actually not bad. Look, over the past 2 decades, Ethiopia has experienced a significant expansion of higher educational institutions, but no research facilities, although research resources are more limited. There is a growing scientific community working in both theoretical and computational physics. The computational and statistical physics lab in Addis Ababa, in which we are working in collaboration with Professor Mulugeta. There are different groups working on different topics, but our group is working on the non-equilibrium phase transition with main theme of non-equilibrium statistical physics. Now, with that brief introduction, let me now move to the scientific part of the seminar and discuss non-equilibrium phase transitions. The outline of the second part includes 4 sections. The first section is the introduction, which focuses on the motivation why deep learning. Second, we move to model and method. The third section is the main results. Finally, we conclude the talk with a summary of main results. As an introduction, while equilibrium critical phenomena are well understood, non-equilibrium critical phenomena remain less understood. Of course, there are so many efforts and substantial contributions, but non-equilibrium phase transition remain less understood. It's obvious non-equilibrium systems are more complex compared to the equilibrium system. However, advancements in computational tools like machine learning provide a data-driven approach, and this is the point of our motivation. According to recent studies, deep learning can take phase transition without explicit knowledge of order parameters. Or we can say machine learning can automatically identify patterns in large data systems. In our case, we apply CNN, meaning convolutional neural networks, to identify and classify non-equilibrium phase transitions. Because CNN is particularly effective for image-like data, and the spin configuration can be interpreted as images. The image of dog and the cat means that a simple CNN which can detect the image of the dog and the image of the cat, or classify images into image of dog and cat. In the same manner, we can use or we can customize this model or adopt to classify spin configurations into two states, like ordered state and disordered state. When we see the second section, we consider Ising to the ferromagnetic system on square lattice with size L, consisting a spin variable Si taking the value of plus or minus 1, that means up or down. Then introduce the standard Hamiltonian describing ferromagnetic interaction as usual. Then we want to introduce an effective interaction parameter and modify the Hamiltonian. This is the energy related to the modified Hamiltonian. And the energy function is defined as a function of h, 1 plus h, multiplied by E naught, where E naught is related to the expectation value of the usual Hamiltonian. Therefore, we have two cases for effective value of h between -1 and +1. Setting h is equal to 0 means removing the modifications. So this is the standard equilibrium Ising model, satisfying the tailed balance. For effective value of h different from 0, this is the motivation to set up the system with effective Monte Carlo dynamics, which intentionally breaks the tailed balance. With this introduction, now we see we use two Monte Carlo dynamics that are well known, namely Metropolis and Glauber update rule. We use the standard Metropolis rule for the equilibrium scenario and generate equilibrium spin configurations, then save this spin configuration in the directory training data set. Next, for the non-equilibrium scenario, we use effective Glauber dynamics to generate non-equilibrium steady state configurations. and save this data into test data set. In this context, Monte Carlo simulation means data preparation stage in the machine learning procedure. So the goal of Monte Carlo simulation is to prepare data with supervised learning in mind. Example of spin configurations for two scenarios, for the equilibrium and non-equilibrium steady state configurations. We use the equilibrium configurations to train the model later, and we evaluate the model on non-equilibrium steady state configurations. And for supervised learning, the trained data set can be saved in two subdirectories in ordered state and disordered state. Ordered state means spin configuration with temperature less than the critical temperature. And the disordered state is, these are spin configurations for temperature greater than the critical temperature. And we confine the critical region, means that for T is somewhat close to the critical temperature from both sides. In this region, we expect a point of maximum confusion, and this point of maximum confusion helps us to determine the critical temperature. For your information, the critical temperature of the equilibrium configuration was solved in 1944. Then we use these spin configurations to train the model. The example of the architecture of the model, CNN, I mean, we can see we focus on the input layer and the output layer. The input is spin configurations. Therefore, the input shape means the shape of the spin configurations. Whereas the output is the probability distribution, and the last dense layer has two nodes, meaning that one for the ordered phase, the other for disordered phase. Then the probability distribution can be plotted. Therefore, we find two curves. One curve is for ordered state, the other curve is for the disordered state. Then the two curves intersect at some point. That point is point of maximum confusion, or we call it crossing point, and that's the critical temperature of for a given lattice size. Before presenting or showing some example of results, we can see the summary of deep learning framework. There are 4 key steps: data preparation, model construction, model evaluation, and analysis. Data preparation is simply performing Monte Carlo simulation for a given lattice size. This includes generating equilibrium configurations, then labeling the temperature, and then generate non-equilibrium spin configurations. Model construction includes training, building the model, training the model, and validation. Model evaluation means testing the trained model on non-equilibrium spin configurations. Then we locate the transition temperature just using the probability curves. Finally, analysis means the language of statistical physics, finite size scaling. And data analysis includes repeating step 1, 2, 3 for the various lattice sizes. And then this various lattice size help us to determine critical temperature in thermodynamic limits and extract critical exponents from data collapse. Just for your information, we cannot discuss the model construction in detail because of time constraint. For your information, the Adam is the optimization. Categorical cross entropy is the loss function. We use a ReLU activation function in the internal parts of the layer, but we apply softmax on the last state layer so that the output for each sample is probability distribution of what the output is. Here is example of the results for the equilibrium scenario. H is equal to 0. Actually, this is a cross validation. And for various lattice size, for non-equilibrium, we should have to perform this for various parameter H, but here the example is shown for two parameter values for 0.4n minus 0.4. As you can see, for all lattice sizes, the curves cross at point of maximum confusion, but the point is vary for different H. This crossing point identifies critical temperature, but which varies with the lattice size, and this is expected from finite size effects. The crossing point means the critical temperature for a given lattice size, and we use this information to perform finite size crossing using fit linear regression, and then we determine the thermodynamic limits as summarized in the table. From the table, we see that the deep learning, the CNN output, compared with the Monte Carlo calculation, and the results are almost in agreement for these two H values. Next, we're using the results for the various lattice sizes. Here is scaling collapse. From the data collapse, we can determine critical exponents, and the critical exponent is determined using the deep learning is almost in agreement with the theory, meaning theory means the theoretical value for equilibrium to the Ising model. So what are the key findings? The model trained on equilibrium configuration can successfully classify an equilibrium as steady status. This demonstrates universality learned by the network. And what physical interpretation? The model learns spatial correlation, and the equilibrium trained network can recognize an equilibrium critical phenomenon. But to conclude this, the calculation for 2H values are not sufficient. We have to perform this for various H, and here is the result. From this result, we can conclude that CNN generalizes from equilibrium to non-equilibrium system almost for all H's. Here is the animation. Yes. What about the time?
Did you finish, or there is something yet? You are in time anyway.
What minute? Okay. So, acknowledgement for the Dr. Mulugita Bakkala is associate professor, and there are so many individuals working in this lab in statistical and computational physics lab in Addis Ababa, and Professor Balaide is the chairperson of the department. Professor Picard is former chairperson. Thank you for the organizing committee of the society. We also thank the International Science Program for supporting this lab. So
Okay, if you are finished.
And now this slide, there is a problem with this slide sharing.
Okay.
Yes.
We see black.
Yeah. Almost finished. Yes. Thank you very much.
Okay. I guess you are done.
Yeah, I've done it. The last slide is not displayed. I don't use it.
We cannot see it. It's at least I see everything black.
Yeah.
Okay, but you want to try again? Yes.
I can't display the last slide. Sorry. Thank you very much.
Okay.
Patience.
Okay.
Thank you for your attention.
Thank you very much for the nice talk. So let's see if there is any question. I don't see any.
Yes, I have a very small question.
Yeah, thank you. Thank you, Rangopal.
Sorry, I think missed something. What is this NESS?
Yes.
How are you defining this non-equilibrium steady states?
Yeah, non-equilibrium steady state would define this state which breaks or violates the state balance, which means by introducing the parameter h, and then there is the Glauber dynamics with a single speed update rule, and therefore, while the standard Metropolis respected the state balance, and this one violates the state balance, therefore, system evolves to non-equilibrium steady status. And as a result, we can generate non-equilibrium steady state configuration using this update rule. We update the spin, meaning we flip the spin using this expression. And this creates the state balance.
Thank you. I got it. Thank you.
So at each step, let's say you compute the variation of energy in the standard Monte Carlo, and in
energy change,
and you add
energy change to flip the spin. To flip the spin, energy changes.
Yeah, energy change, and then you add this extra quantity, h times.
Yes.
And this is not simply adding a constant to the energy, no, because it's different at any step.
No, we do not. Simply this is the energy due to a single spin flip, the energy change. The knowledge of specific energy value is not important to flip the spin. We need only the value of the energy change. Because of a single spin change, the whole configuration, other spins are the same, only one spin flip, and therefore we can calculate the energy change.
Okay, thank you.